then we could see a cyclohexane ring just like that. And if I hold it like this, do you see how you have a purple atom sticking out at you? And so what would you do? You just go a wedge with purple, okay? So that's one representation of it. But I taught you guys in the videos the chair conformation, where you draw those two horizontal or those parallel lines like this. So how in the Sam Hill does this look like that? Okay? And the trick is when you take your model and viewing it like that, now you have to turn it to the side, perpendicular. And my model's really tiny, so I apologize, but if you look this way, you can see that there's a zigzag to it. Okay? And with that zigzag, you're going to have one carbon down, one up, one down, and it alternates. And that's what we see up there. So when you look at it from that perspective, and what you're looking at is not the red, white, or purple atoms, you're just looking at the black atoms. The black atoms represent that chair. And a chair flip, very, very important concept here. A chair flip is not the following. You see how I just rotated it in my hand? That is not a chair flip. What I want you to pay attention to is the purple atoms here. When I do a chair flip, what's happening is the bonds are twisting. Just like that. Do you see how I didn't rotate the molecule? I just twisted the bonds. And now where are those purple bonds? You see they're in the plane. So when you have these white atoms or these hydrogens, are those axial or equatorial? Those are axial, and then the purple atoms are all equatorial. And what happens to the purple atoms when we do a ring flip? They go from equatorial to axial. All the atoms do that. And so we have a ring flip. That's what it is. All right? And so when we do a ring flip, something that's often confusing for people is when we put a substituent on it. Let's say we put a substituent, let's put a methyl group right there. And we'll have a hydrogen there. And then let's put a equatorial CH3 right here. What does the chair flip look like when you do that? So we would have to draw the parallel lines in opposite directions than I did the first time. You saw how I drew these very first, right there and there. Now I draw them in opposite direction, like that. Okay. Now when we do a chair flip, what's happening? This carbon is coming up, and this carbon is coming down. So if I numbered these carbons, and I'm not numbering them in any special way, I'm just putting down numbers, okay? I'm not trying to name the thing. 1, 2, 3, 4, 5, 6. Where is carbon 1 on the right side? Right there. 1, 2, 3, 4, 5, and 6. So we see that we have a methyl group on carbon 2, or let's change it so it's easier to talk about. Let's go ethyl group on carbon 6 and a methyl group at carbon 2. So in form A, the methyl group, the CH3, is axial or equatorial? Axial. The way that we know that is we take a good hard look at the carbon. Do you see how that it's an apex pointing up? And so when we look at that apex, we have a bond that comes straight up off of that. And then we have an equatorial bond. And look at how I drew that equatorial bond. It matches the bond angle of the adjacent, not the bond directly connected to it, but the other one. You just skip a bond. And so that's an equatorial bond right there. So we could say equatorial, and this one is axial. Now with regard to carbon 2, that apex, do you see how the methyl group is pointing up? And if that's pointing up, then that means the equatorial one is pointing down. Follow so far? Now if we analyze carbon 6, we have what? This bond right there is doing my best to match that angle right there. And that is an equatorial bond. Because we have what? A hydrogen coming straight up. Do you see the apex right here? That carbon right there? What is it? It's pointing up. Okay? And so we have this hydrogen right here. That's axial, equatorial. But now we have axial up and equatorial down. Let's add one more so we can compare and contrast. What if I put, let's clean that up. What if I put something like a hydrogen there, and let's put a green methyl there. Now look at that carbon right there. Do you see how it's pointing down? And so this methyl right here is still axial because it's going straight down with that pointed carbon. So this bond right here is straight down. So that's down and axial. And this is an equatorial bond that is pointing up with respect to that pointed carbon. So that is up and equatorial. So you cannot try to make shortcuts that axials are always up or axials are always down. You have to look at the reference. You have to look at the carbon. Is the carbon pointing up like so? And if the bond that goes straight up, that's axial. If you have a bond that's pointing down, the bond that goes straight down is down axial. Okay? Axial up. Now when we do this ring flip, we see that this black methyl group is on carbon 2, and it is axial. So what does it have to be on carbon 2 over on molecule B? It has to be equatorial. So now it just begs the question, what does equatorial look like? At carbon 2 right here, we've got to connect that bond there. Well, what would axial look like? Maybe that's the best way to do it. Axial would be straight down. Okay? And then equatorial is going to skip this bond and take a look at the second bond. You see that bond angle? And so that's the bond angle we need to draw. So that methyl group right there is what? Equatorial. The hydrogen is axial. So you see how those switched? Those completely swapped. But does the notation of up and down change?
No.
No, it doesn't. Because when we take a look at this carbon right there, it's pointing down. And so this hydrogen bond right there is axial down. And then this bond right here is equatorial up. So the ups and the downs stay exactly the same before and after a chair flip, but the axial and equatorial bonds do change. Okay? And so if we finish this out, where would our green methyl group go? Well, that's attached to carbon 1. So we have what? We have an axial bond and an equatorial bond. Where does the methyl group go on molecule B? Axial or equatorial?
Equatorial.
It would have to go equatorial, so CH3 here and the hydrogen there. Do you also see that this green methyl group is still down with respect to that carbon there? So let's take a breather. Is that making sense? Do you guys have any questions? Or are we just trying to write down the information and try to absorb it later? Yeah. Okay, and then the last one, the ethyl group. Ethyl group is attached to carbon 6. So what do we have? We would have an equatorial bond this way. Well, let's change the color. We have an equatorial bond this way and an axial bond that way. Where's our ethyl group over here? That is equatorial, so that means it has to be axial in the other one. And that's axial down. So you see the axial and equatorial changed, but the down and down has stayed the same. Okay, so why is this so important? Is because I'm going to need you guys to be able to interchange between the structures. If I draw the skeletal structure, I need you to convert it to a chair. And then if I give you a chair, I need you to convert that into a skeletal structure. Go back and forth. So let's practice a little bit on that. Okay. So I'm going to give you guys a few minutes. I'm going to draw a skeletal structure, and I want you guys to draw the two chairs that correspond to it. And then between the two chairs, you need to tell me which one is the most stable. At equilibrium, which one would be more favored? Okay, so let's draw. There's our ethyl. And there's a methyl. Me for methyl, or you could do CH3. It's all saying the same thing. So I need two chairs that match this. Now, I'll let you guys try it, okay? And then I will teach all the other things that we need to talk about. So draw the two chairs that correspond to that structure. Let's see what you can come up with. I'll give you 5 minutes.